the first rows as fast as possible. And it can be a completely different approach by means of execution plan to get this, to achieve this goal. And so if the same SQL statement, the same SQL ID, the same hash value is parsed in another session with a different optimizer mode, it can't reuse any child cursor created by the first session. So we are ending up with another one, maybe with the same execution plan, but with a new child cursor. Another stuff is NLS, or user identity trouble. NLS, for example, if your native language support configuration requires a different sorting, for example, how to sort those German letters with dots, ä, or any special characters for special languages, it might be a different approach. The same reason for optimizer mode change. And user identity trouble. This is something quite funny, but imagine you're having the same table name in two schemas, and you're doing the same select. It's the same hash value. So it's looking like we would use the same execution plan for the second execution. It might be a problem, because the execution plan may not be true. And so if you're switching the user context back and forth, it will always invalidate your child cursor, because the hashing algorithm of Oracle doesn't involve the schema name. So if you're using the SQL in a different schema and you're hopping back and forth, you're always invalidating the previous cursor. For example, if you have your test system or a development system on your production machine, on a different schema with different resource management, but you can end up with invalidating the productive cursors. So be careful if you do not isolate by means of shared pool. Another thing is outline mismatch or cardinality feedback. Cardinality feedback was explained on the previous slide, and for the same reason, cardinality feedback might give you another child cursor. The stored outline or profile or whatever will do the same, because if we are changing a profile, we want to change the execution plan, and the way Oracle to tell that we want another execution plan is to invalidate the cursor or do not reuse it. So this is something we want, and this is one of the major reasons in 11G why this feature is propagated and is used widely. Some unwanted reasons for invalidating cursors is bind mismatch. There are many sub-reasons, and it's most unwanted, and I want to explain it a little bit more in detail, because this was something that was breaking my neck some years ago. Let's have a look at adaptive cursor sharing. If you're adapting, you have got one shared pool entry or more shared pool entries, more library cache objects. If we are optimizing for invalidation reasons or for the first time, we are inserting one child cursor. And if the sequel bears some problems as described on the slide before, we will end up with one more child cursor for another reason. If adaptive cursor sharing sees in shared pool that we have more than one child, it cannot do a soft parse anymore, because a soft parse simply ignores everything that's in the statement, as well as bind variables. So if in 11G, as soon as we have more than one child cursor entry, as soon as the statement is bind where, we have to parse a little bit harder. It's no hard parse, because we do not do the whole optimization process in advance, but it's harder than doing just the reuse a SQL ID that exists in the library cache. And the harder soft parse involves bind peaking again, because we have to look up the selectivity of the given bind variable. And from the point in time when you have more than one child cursor for bind mismatch, for cardinality feedback or other reasons, you always are doing a harder soft parsing. The process. You have got a library cache object, it's the parent cursor, it's bind aware, and you have got several child cursor entries. And the statement let's assume, is binary. The SQL statement issued against the database will be hashed and compared to the parent cursor. It's the well-known shared pool check. And then we have to peek. We have to peek the bind variable. And if we can reuse an existing child cursor, it's holding a shared mutex and accessing this child cursor. If we are peeking and find, okay, the selectivity is nothing we can help with an existing child cursor, we have to optimize it again. It's a hard parse again. And if we are doing a hard parse, we have to hold an exclusive mutex for this object because it's an incompatible operation. I will detail this in the next slides. So, what's a mutex? If you are talking about mutexes, we have to know the basic reason why we need serialization. This is a famous example. It's a singly linked list. The singly linked list, if I want to remove an item from a single linked list, I remove the pointer pointing to it. So in the second row, you see there are two removing operations at the same time. So this vector was indicating to I, and this vector was indicating to I plus 1. And so when we are removing two items at the same time, we are ending up with I plus 1 not removed. This is a classical race condition. We've got two concurrent operations, and we have to serialize them if we want to avoid this effect. No, not two people should be able to manipulate the linked list at the same time. And this example is quite good for the library cache, because the library cache objects we've been seeing here, this is organized as a linked list. So this is not far from practice here. The mutex is called a mutual exclusion. It's just another word for a serialization item. In Oracle terms, it's like a latch, but faster. The reason why it's faster, it's not realized in software anymore. As far as possible, Oracle is using operation system-based mutex functionality. For example, on Linux, it's possible to use very basic mutex technology from kernel calls and from the processor. So when we are talking about mutexes on Linux, we are talking about direct processor operations, so it's very quick and consuming very little overhead. The difference in Oracle is that latches traditionally have been protecting a large amount of objects, and mutexes are more granular. So I do not have 200 objects for one latch, but I have 5 objects for one mutex. So it's reducing the risk for false contention. False contention is always when I'm contending for a mutex because I need another object when the one is locked. So in 11G release 2, the mutex concept was introduced, and I've been talking about doing mutexes by using CPU calls. There are several platforms that do not allow or do not provide generic mutex processing by CPU. For example, the AIX boxes power architecture from IBM, and in this case they are RISC processors, and so they do not have calls for that. And in this case, the kernel generic mutex module of Oracle is emulating them. I did not see any performance issue when using RISC processors. We are using 50% of our customers we are shipping 50% of our products for IBM AIX, so it's no disadvantage. It's just a different solution. So this is mutex contention. If you are looking at my library cache object, it's a cursor of any kind. It's protected by a mutex. Let's assume it's a single mutex, but it doesn't matter really. Session number 1 is manipulating the library cache object and thus is holding the mutex in exclusive mode. Session number 2 has the same plan. it wants to manipulate the library cache object, but can't get the mutex. If it tries accessing the mutex, it has to spin on the CPU and try. But if session number 1 would release the mutex, session number 2 would like to have it as soon as possible. So it's always spinning on the CPU for that. And if it's spinning on the CPU, it's using the CPU and the CPU is burning, and nobody else can do anything useful with it at the same time. So mutex contentions are basically eating up your resources, and this is why we do not want it. For the same reason, Oracle implemented a spin count. And the spin count on the Oracle database makes releasing the spin after a number of loops. So, for example, if the spin count is 1000, after 1000 attempts, the session number 2 stops contending for the mutex and goes off and sleeps. And as soon as it's sleeping, it's recording a wait event. If it's spinning, it's not recording a wait event. If it's spinning, it's displayed as CPU time, and if it's sleeping, it's wait time. So the time you are seeing in the wait interface of Oracle is not the time we are spending on the mutex. It's the time we are sleeping because we did not get it. This is mutex contention. A wait event on the mutex is somebody requests a mutex, cannot get it by spinning, and thus is sleeping. So the little conflicts below the spin count you can recognize when you're looking into the wait interface. Sleeping is not recorded as wait time. Sleeping is recorded as wait time, and spinning is not recorded as wait but as CPU time. There are different mutex wait events I want to talk about. The first one is mutex exclusive, mutex X. Mutex X is always held for a library cache object if we want to build a new child cursor. So if you are changing the chain, it has to be disconnected and inserted a new item. So in the meantime, nobody should do it again. When we are capturing SQL bind data, so during bind peak, for a short period of time, the library cache object has to be locked because the result of the bind peaking has to be recorded into this RAM structure. And if we are modifying cursor-related statistics, hit counts and so on, then we have an exclusive lock and nobody else can manipulate it. This is a manipulation mutex, for usage and manipulation mutex. We will see another type as well. Another manipulation and usage mutex is the shared mutex. Wait event. When I want to have shared access to the mutex, or whenever I'm using the library cache object. Using is basically a read operation, but every time a new session, a new parsing process wants to access this very same SQL ID, it's getting in flux. And flux means that we are changing the list of processes that are interested in this mutex. So, not in this mutex, in this library cache object. So for this library cache object, we've got an interested operations list, not a transaction list, interested operations list, and this list has to be changed as soon as a new session comes into the pool. So we need a short time of shared mutex holding here. It's a small wait event, but I just wanted to show you what's used for. This is another category of mutex holds you can see in parsing. It's pin. Cursor pin means that I do not want it to be removed from the library cache. It's a different thing than using it. Removing always happens when it's aging out. For LRU algorithm is considering it as being owed. I definitely do not want to have it aged out when we are creating the cursor and when we are altering the cursor. Creating the cursor is always in the plus side of LRU, but if you are altering the cursor, it would be a disaster if the memory structure is concurrently killed by another process by cleaning up. If you have a shared pin mutex hold, it's always necessary when you are executing the cursor. If you are executing the cursor, we definitely do not want to have it aged out as long as it's in use. In a very heavy loaded environment, it can be the case that every mutex, that every library cache object in the library cache is used from time to time, or is used all the time. And it's no sense in aging it out as long as we are using it. And a special wait event is pin S on X. Pin S wait on X. It means that somebody has it in shared mode, but somebody wants it in shared mode, but another one has it in exclusive mode. So somebody is altering the cursor, and another one wants to use it. And those two mutex locks are not compatible. So as long as somebody has it in exclusive mode, nobody else can get it in shared mode. So the shared guy has to wait for the exclusive guy. And because it's a special situation, Oracle is providing a special wait event for that. It's not another kind of mutex, it's always the same structure. It's not another thing, but the wait event is recorded differently to help us diagnosing this issue. So, some practical things. I want to show you how to reproduce cursor pin S wait event. It happens when we are massively parsing one SQL ID. As you remember, we are hard or soft parsing lots of stuff. We are soft parsing lots of stuff. And we are experiencing a hotspot object. The library cache is hidden on the same spot, on the same mutex for all the time. And you will see this in Oracle wait interface. The solution to avoid the same SQL statement to hit the same the same library cache structure all over again might be to diversify your SQL text and thus your SQL ID. It's not a very nice solution, but it can be a solution to give you a rough idea of what I'm talking about. Just a remark, here inserting the hostname here might be a hack for a web interface solution with 200 web servers. Then you will have 200 different SQL IDs, and you are spreading your accesses over 200 mutexes, hopefully. Mark Farnham asked me to tell you that this solution might not work for every wrapping structure. So if you're using Java, it works brilliantly, but there might be other languages that do not recognize block comments. So maybe consider line comments with double dashes. Might improve your experience. This is the provocation. On my blog you will find a white paper to this presentation as well that details those experiments in PL SQL to reproduce these issues. I was looping one SQL a million times in 20 threads in parallel. So I was stressing the database. And we are just, in this way, we are just overcrowding the pin mutex. And so you see the CPU time, it's executing, parsing, whatever. And this little cream on the cake over here is the pin S wait event. If you see this in production, I'd say the pin S is not your problem, but it gives you an indication where to look for. And this is the main purpose of a wait event. Wait events to look at are not always the big you see. Also the small ones in wait interface can enlighten you the problem. So do not concentrate on the big wait events. Look at everything and try to understand. A more complex example is the mutex shared or mutex exclusive wait event. It's not, the last example has been pinning in memory, and this one is usage. Usage of the mutex wait event for protecting against manipulation. Basically, if you see this element, you are invalidating library cache objects frequently. So, as a result, you will end up with too many cursor objects in library cache. If you're frequently invalidating, the list grows and grows and grows. Again, the diagnosis will be the oracle weight interface. For the first glance, it's your first chance to see what's going on. To see more details, you will need to involve a 10046 trace level 12 to see bind variables, to see data types of bind variables. I will show you this in detail. And the $SQL shared cursor weight event shows you the reason for the invalidation. Remember the 64 reasons why cursors are invalidated. This view gives you an impression where it comes from. But $SQL shared cursor in 12.2 was a little bit buggy and is still a little bit buggy. So if you need real information, involve a cursor trace following this metalink node. Cursor tracing can be nasty business if it's happening many times, but there are methods to narrow it down. Just have a look at this node. It's much too much to talk about within 45 minutes. But it's good handicraft to use both sources and do a solid diagnosis of the problem, because you will have to go to the developers. If you're DBA, you will have to go to the developers and tell them, hey guys, there's something going wrong, and they will ask what, and this is how you can find out. For an example reason out of my practice was that we are using JDBC, and using JDBC for setting bind variables involves a set method. It's set number. There's no discussion. It's a number for integer or number data types, and the bind variable data type is number in this case. But if you're resetting it with set null defaults to data type varchar2. So for the next execution, the bind cursor is invalid. And this, if you're setting the bind variable to 5 with data type number and resetting it to null, you're ending up with two cursors for the same operation for the same SQL statement. But the difference is the value you're setting in the bind variable. The reason in SQL shared cursors is bind mismatch. This is the diagnosis on 10,046 trace. This is the bind variable number 2 and the bind variable number 2 from different executions, from different trace files. And you see the OACDTY is 01 and this is 02. This means the data type has been different, and this is the only difference between those two things that is important for the cursor, for the library cache. Now imagine if you've got the case, you've got 10 or 15 bind variables in your SQL statement, in the work condition, for example, or wherever, and you're changing the bind variables frequently, you're ending up with combinations. And if you're frequently setting and resetting the statements in different orders, you're ending with 2 to the power of n child cursors. And 2 to the power of 30 is way too much for most database servers I know. In my case, the death happened at 3,000, and it's way less than that. And it was a 16-core machine. So have a look if you're using bind variables and resetting them. A quick fix for a DBA that can't do anything for the application, change the JDBC, change the code they are using, was to flush out this cursor frequently. It's absolutely mess if you're flushing out stuff out of the library cache. It won't work if you're flushing the whole shared pool, because you're ending up with with parsing issues. But if you're flushing out one particular SQL statement, you're reducing the number of child cursors frequently, because the list starts from 0 again and again and again. It's dangerous if the problem comes from the only user of this SQL statement, nobody will complain, because you won't make things worse for this guy, because this guy is parsing anyway all the time. But if the statement is used by the app user and a real user, he will have to parse all the time as well. And maybe he has been holding only 1 or 2 child cursors and using them frequently, and if you're starting to flush it out, he will have to reparse and reparse again and again, and he will complain. So this is no long-term solution. This is a solution to fix it and to try if you can fix it, and for the most times it's better for the customer than doing nothing. In my case, it was necessary to flush it out every minute, because within a minute or 2 I created 400 to 600 child cursors, and by 3000 it was the nexus. So I had to keep numbers low in this case. Long-term solution for this problem is to know that setNull accepts a data type. So if your developer doesn't know, tell him. If you're not invalidating the cursor by setting to null, you have got no child cursors, no more than 1 for this case, as long as the execution plan doesn't change. So this is the long-term solution. In my case, we had to work for 5 days with a workaround. If you want to provoke a situation like that, it's not simple, because in PL SQL you are forced to use the right data types. So there are methods to do that. Just have a look at the paper. I will put it online until lunchtime. If you're generating 64 child cursors, it was a 16 CPU machine. So this is number 16. I was accessing them 20 times in parallel, and was ending up with CPU time. Okay, we are pausing it. We were ending in a library cache mutex that we have not been discussing in this talk, but it's the same thing when you are changing library cache content lists and stuff. You have to protect it as well, and this is why this wait event exists. And these are our wait events we've been talking about. This is mutex exclusive here, and this is mutex shared here. And we see that we have a delay when we want to create new children. And this is a problem for everybody that is parsing frequently and wants to create a new child cursor and can't because another one does. So we are blocking each other by the same problem. And if somebody does not parse and tries to select a child that fits, he can't get a shared cursor because another 100 guys have exclusive locks and are enqueuing for exclusive mutexes here. So you're ending up with 3 problems by one reason. Sad to say, there's a similar problem if you're using varchar bind variables. A bind variable is categorized. Bind buffer sizes are 32, 128, 2000, and 4000 bytes. If you are below a border, you are using this type. So if you are using 30 bytes for the first execution and 120 bytes for the second execution, you're invalidating the first cursor. And hopping back and forth will always invalidate the predecessor. So the same problem as I described for the numeric bind variables, for the difference that we have got 4 possibilities. Not only number and varchar, but we have got size 1, size 2, size 3, size 4. And so if you have combinations of bind variables in the same statement of type varchar and changing lengths frequently, you're ending up with 2 to the power of n child cursors and have the same problems than before. The reason is different now. It's not bind mismatch. It's bind length upgradable in a $SQL shared cursor. And I can't give you a solution for that, because it's coming from the application. If the application is shipping longer binds and shorter binds, there's nothing we can do about it. And there are cripple solutions. You can pad the bind variables by blanks, you can do whatever, but you can't change this behavior. But maybe it's progress to understand it. And this is why I'm talking to you. nothing I've been talking about was very nice, but this is worse. There are several features in Oracle that doesn't make life easier. When we were migrating from 10 to 11, to 11.201, there was a change in Oracle software that was not documented. So in 10G, it wasn't possible to have more than 1024 child cursors for one parent. In 11G it was. And so the list in library cache could grow and grow and grow. And if it grows, it's taking more time to select the right child cursor. And this was removed in 10G because they wanted to make their code quicker. I think it worked, but it didn't work for me. Oracle support told me that we are not longer obsoleting a parent cursor when it reaches X child cursors. Soon afterwards, we had an enhancement patch with an underscore parameter, cursor obsolete threshold. It was default to 1024 as before, and in 11.203 it's included. So if you have an issue like that and cannot solve it by root cause, you can at least go to the most recent version or apply this patch. Then you're invalidating the cursor after 10,024 child cursors generated. Then you have to reparse it, and you have to pay for the reparse, but then you work for a limited time again. In my case, it would mean reparsing every 3 minutes. Hard parsing every 3 minutes. Other internal pitfalls in connection to the library cache is those two bugs. They are related, but not the same. They have a memory leak in the structure of using in the library cache. So if you are stressing the shared pool, the number of unused child cursors will increase and increase and increase slowly over days, sometimes over weeks. But in the end, you've got a vast amount of child cursors, and you have to pay for it by concurrency all the time, as explained before. In 11.203, there's a fix for that, and as a backport from version 12, and in version 12.1, it should be fine. The other bug here is that the SQL shared cursor does not report the write wait event, and the wait interface does not report the write wait event, and nothing does. No trace, nothing does report the correct distinction between mutex S and mutex X. And this is the official workaround until you can go to 12.1. Just don't believe it. Okay, a quick summary. We've got 3 minutes left. My suggestions for cursor mutex S or X casualties. Check how your application is using bind variables. I don't say check if. I know you do, because if you don't have those problems. But if they are abusing bind variables, check why. Reduce the number of cursor versions in your application for one particular SQL statement to below 100. Then you are safe. This is a rule of thumb, but I was working good with it. Do not believe that all faults are your faults. Check if your RDBMS has bugs, because they are common. And go to 11.203 if you're on 11.2. 11.202 was no improvement. Go to 203 if possible in any way. More resources are this support documents, cool presentation from Tamil Poda, the book of Craig, and the blog entries on mutex waits from Andrei Nikolaev. They have been great sources, and they have been a great help for questions in this case. Thank you very much for your attention. We've got 2 minutes left for question and answers. If I can clarify anything, just ask. Thank you very much. I can hardly hear you. Just come up in front and cover it.
The address for downloading?
Yeah, I switch back to the address.